This video looks at sequences. What is a sequence? It is a function whose domain, and we're going to use the letter n, not x, but domain is the set of positive integers. Another name for positive integers are the natural numbers. And the reason why they're called the natural numbers is think about how many fingers and when you started counting. You started counting on your fingers and you started with the number 1, not 0. And so natural numbers start with 1, 2, 3, and go on up. And that's probably why we use the letter n. But let's go back to our definition. A definition. The sequence is a function whose domain is the set of positive integers. In other words, it's just a list, and that order matters. So we have a listing, so we use commas. So we have lots of subscripts, notation here. So a sub n is the nth term of the sequence, and it's denoted with the braces. And so that's going to give your list of the elements in our sequence. So we're going to start out real basic, no calculus whatsoever, just get used to this notation, is write out the first 4 terms of the sequence. In other words, you're going to let n equal 1, 2, 3, and 4. All right, so a sub 1, the first term, is going to be 2 to the first minus 1 over 2 to the first. So just really easy arithmetic. The second term is going to be 2 to the second minus 1 over 2 to the second. Again, everywhere there is an n, I'm replacing it with the given value. So this is going to be 3/4. The third term, 2 cubed minus 1 over 2 cubed, 7/8. And the fourth term is 2 to the 4th minus 1 over 2 to the 4th is 15/16. Now the reason why I asked you to list out 4 terms is just so you can get used to the notation, but also you can kind of hopefully see a pattern. And so that's why the next question says, what do you think the limit is as n approaches infinity? As you look at these numbers, we want a half, 3/4, 7/8, 15/16. Is it approaching a value? If you can't look at it in terms of fractions, think about decimals. This is 0.5, 0.75, 0.875, 0.9375. What do you think it's getting closer to? Hopefully, you see that the limit, it's getting closer and closer to 1. And this chapter, we're going to be looking at lots of limits and asking ourselves, does a series or a sequence, and yes, those are something different that we will learn about, do those converge or diverge? A sequence agrees with a function at every positive integer if f of x, and remember x is the set of all real numbers, if f of x approaches a limit as x approaches infinity, then the sequence must converge to the same limit. If the limit as x approaches infinity does not exist, then we would say the sequence diverges. Just think about what that is saying. It's relating a function to our sequence. So this kind of goes to our theorem. If we let L, which is going to be a limit, be a real number, and we let f be a function of real variables such that as x approaches infinity of our function approaches the limit, then we can say the associated sequence such that our function of n, natural numbers, then that limit is the same as L. In other words, a function of all real numbers can be associated to a function of the domain of natural numbers. Why is that good? Why is that useful to know? Why do I put in this theorem? Well, it's useful because we can now use what we know about limits of functions for our sequences. So let's see how we're going to apply that. Again, not real difficult. We're going to be asked, does the sequence converge or diverge? Does it get smaller? Does it get bigger? If it converges, what does it approach? What is its limit? So think about limit rules that you learned from Cal 1 and L'Hopital's rule that might come into being. All right, so the first thing you could do is you could just list out a few terms just so you can kind of see if there's might be a pattern. And that's what I'm going to do. So a sub 1, that's going to equal to negative 2, because that's 2 times negative 1. The second term, that's going to be positive, because now that's squared, so that's going to be 3/2. That's going to go back to negative. I'm going to do one more, and it's going to go back to positive. So right now I just see this oscillating back and forth, back and forth. So if you were to look at a graph and we were just plotting the x values, I'm sorry, the y values. So we have x is 1 or n is 1, 2, 3, 4. What do we have? We'd have negative 2, then positive 3/2, then negative 4/3, and positive 5/4. What could it be doing? Well, now let's go back and look at the calculus. Coming back here. Okay, what did we learn? As n approaches infinity, what's going to happen to that fraction? It's going to go to 0. What's going to happen here? It's just going to go between negative 1, positive 1, negative 1, positive 1. So what can we conclude? We can conclude that this diverges, and I'm going to go ahead and put a reason, because it oscillates between negative 1 and positive 1. So my picture over here is probably a little bit misleading. It didn't get smaller and smaller. I think what's going to happen is it's going to go from positive 1, negative 1, positive 1, negative 1, positive 1, negative 1, as n approaches infinity. So again, we've answered the question. It diverges, and we can look again at the calculus as we take the limit as n approaches infinity. In fact, I want to go ahead and write that and say the limit as n approaches infinity of a sub n does not exist because it oscillates. Okay, so let's look at this example. That looks a little bit scarier. I'm not going to go ahead, you could list out some terms if that helps you, but let's go ahead and take the limit. Well, let's see, if I look at the function that might be associated with, and rewrite this as 2x plus 1 over 1 plus 3 x to the 1/2, remember the square root 1/2. And I said, well, what is the limit as x approaches infinity of this function? What do I know about that function? You could use L'Hopital's rule, but go back to Cal 1 and ask yourself, if I have x to the first power on top and x to the half power on bottom, what happens? If I have a higher power on top, what's that limit going to be? You should have learned that it does not exist. Or we could say this diverges. And since the function diverges, a sub n diverges as n approaches infinity. So not hard, just using some limits, writing out some reasonings and conclusions. All right, so let's look at this problem. So we have the limit as n approaches infinity of n squared over 2 to the n minus 1. Well, if I just kind of look at that limit, I really have it in the form of infinity over infinity, because that's going to get really big and that's going to get really big. So what could I use? I can use L'Hopital's rule. Okay, remember L'Hopital's rule says take the derivative of the top and take the derivative of the bottom. But that means we have to remember how to take the derivative of something like that. So let's take a minute and review that. So if I have some number raised to a power, and I want to take the derivative of that, it's going to be the same thing multiplied by the natural log of our constant. So I'll have the limit as n approaches infinity, and I'm going to use L'Hopital's rule, so the derivative of n squared is 2n. The derivative of 2 to the n is going to be 2 to the n times the natural log of 2, and the derivative of negative 1, of course, is 0. Well, I kind of still have infinity over infinity, don't I? So I'm going to use L'Hopital's rule again. So I'm going to have the limit as n approaches infinity. The derivative of that is 2. And then I'm going to repeat this. So it's going to be 2 to the n times the natural log of 2. And then I already have that natural log of 2. That's just a constant. So now, what's that limit? Well, as n approaches infinity, this denominator is going to get really huge. So our limit is 0. So we can say, therefore, 3 little dots, the sequence converges to 0. Again, really, just finding limits. Let's look at this theorem. It says, as the limit as n approaches infinity of the absolute value of a sequence equals a 0, then the limit of the sequence is 0. So think about what takes about absolute value, makes everything positive. So if you have some negative and positives and they're all getting smaller and closer to 0, then the sequence itself will approach 0. Let's look at number 5. We want to find if does this converge or diverge. So we need to take the limit as n approaches infinity. But why is this theorem here? Well, notice because of that negative, as n goes from odd to even, that's going to oscillate between negative and positive. So what if I take the absolute value of a sub n? Then I'd have the absolute value of negative 1/2 to the n, which would be positive 1/2 to the n. I could also rewrite it as 1 over 2 to the n. That says take a look at the graph. Well, if you take a look at the graph of f of x equals 1/2 to the x power, what does that look like? Maybe you can see as x gets really large, you're getting closer and closer to 0. In fact, as I take the limit as n approaches infinity of the absolute value of n, what's that going to approach? 0. So again, we can say, therefore, the sequence converges to 0. So graphing helps, using your limits helps. Let's look at number 6. In fact, I think I should really have parentheses around here. That should be negative 1 raised to the n plus 1 power divided by n. So again, because I have that negative raised to a power, that negative, when that power is even and odd, it's going to make it go negative, positive, negative, positive, negative, positive. So that's why, again, this theorem is very helpful. So if I take the absolute value of a sub n, this numerator now just becomes positive 1 over n. So if I take the limit as n approaches infinity of the absolute value, what does this approach? 0. So we can say, therefore, a sub n converges to 0.